All right, so now we're going to go ahead and start trying to code out our Crank-Nicholson method version of our heat diffusion equation. So just go ahead. I'm in the same script that we did before, mostly because a lot of the information we have in here is the same. You know, we're gonna have the same variables. Again, we can change them, but why not just reuse them? So I'm actually going to copy and paste a lot of this stuff down here, just so that save us a little bit of time and I don't have to go through all this over again. So we're going to keep all this stuff the same, but the one thing we do have to adjust for is that our R value, if we remember, is now there's going to be a 2 in the denominator. So it's going to be 2 times delta x squared. So that's one little adjustment we need to make. But other than that, we can go ahead and start talking about what we mentioned in the previous video. So when we were at the whiteboard, we talked about using something called solve banded, which is, let's actually just go ahead and let's import this before I forget. So we'll go from SciPy dot linear algebra. We're going to import solve underscore banded. You can go ahead and run that. And let's go ahead and look it up and read about some of the literature. So SciPy, there we go. And here we go. So this is the literature on the solve banded. And what it's going to tell us is we need a few things to use this. The first things are we're going to need these L and U values. So what it means by L and U, it means the lower and upper bands. So if we look at this matrix here, which looks fairly similar to the one we had in the previous video, we see there is one main band, which is the 5, 4, 3, 2, 1. And in our case, that's the 1 plus 2R, or sorry, 1 minus 2R. And then we have our lower band, and we're going to have 2 upper bands. So in this case, L would be 1 because there's 1 lower band, and U would be 2 because there's 2 upper bands. As you can see, that's what they described down here below. I guess actually, before I get too far ahead of myself, what this solve banded is going to do is going to solve AX for B, assuming that, again, A is a banded matrix, which is what we have because we have those nice bands that go diagonally throughout our matrix. So anyways, that is what the L and the U are. And then we're going to need to solve for our AB. So that's right here, that's going to be our banded matrix. And you'll notice AB here is a little bit different than how we had it listed out on the board and how it's listed right here. And the only difference is, I guess one way of thinking about it is that they took this matrix and twisted it 45 degrees. They took everything in the diagonal and they made it horizontal. That's how I like to visualize it in my mind. And when they do this, you get the main band right here, this 5, 4, 3, 2, 1. Again, in our case, the 1 minus 2R. And then you're going to have the upper and lower bands. So here you have the upper bands of the 2 and the 1s, or the negative ones, and then on the lower band you just have the 1s. And these asterisks here, those are going to be the values that aren't included. So if you notice, there's 5 values here, there's 4 in that first upper band, so those are going to be zeros. We could put anything there. I'm just going to put zeros in there for simplicity's sake. And then the last thing we'll need is our B value, which is just that vector that we showed on the right-hand side of our equation when we were at the whiteboard. And this will just be simply solving out an equation, and we'll have to iterate that through to actually get our final result, but that's way down the road. So let's go ahead and just start by looking at creating our matrix. So we'll come down here. Let's go ahead and run these variables. And then we'll go ahead and create some matrix. So we'll say A equals numpy dot zeros. So that's going to create some matrix for, in our case, full of zeros. And we're going to enter in create a matrix of shape 3 by 48 is going to be how big our matrix is. That's going to be dependent upon how many segments we have in our bar. So in our case, we have 50, and then we're going to exclude the two ends because we already know what the temperatures are in those two. Those are going to be set. They're not going to change. So we're going to do nx minus 2, which should be create a matrix of an array shape 3 by 48. So if we run that, and then what we can do is numpy.shape, and then we can do that for the shape of A. And we see that we have a matrix now that's the shape 3 by 48. So we're going to have 3 rows and 48 columns. So if we think back over to this example, here there's 4 rows and 5 columns. So with this, now we need to go ahead and start filling in our matrix. So we'll say that A at that first row, so A of 0, and we're going to go from the second value in our matrix in that first row, so 1, all the way to the very end of that matrix. And that's because, again, if we look back here, that first upper band is not going to include that very first value. So we're going to exclude that first one and then go from there on, and everything there is going to be equal to negative r. Again, that's from the previous video when we made that matrix. So now we can go ahead and do the same thing, but now we need to do it for our main band. So we're going to do it in the second row. So we're going to index that as 1, and it's going to go from the very beginning of the matrix all the way to the very end. And that's going to equal 1 minus 2 times r. So with this, that will complete our middle main band, and then we need to do our lower band as well. So we'll say A, and this is going to be that third column, and then it will be going from the very beginning to 1 before the end. So it'll be negative 1. Again, you can just see that here. It's very nice to see it in this visual matrix. We're going to go all the way up, and then we're going to have that 1 empty value because it is the first band underneath the main band. And that's also going to be equal to negative r. So next, we need to let's first see what A looks like. Let's see if we can. So there we go. That's what we're hoping for. So R in our case, I believe, is 0.25. Yeah, because earlier it was 0.5, and now we're dividing by that 2. So R is now 0.25. We got negative R on both sides, excluding those first and last points. And then that middle is 0.5, and that value makes sense as well. So that's the matrix that we have. And now we need to go ahead and create the right-hand side of our equation, which will be that vector, which will be, we'll just give that the variable name b. And we'll say that is equal to, it's actually going to be very similar to what we have up here. So I'm actually going to copy this over. It's almost identical. So we're going to have the same indexing. It's the exact same indexing as before, except now we have to multiply by different coefficients. So we have to multiply this first one by r, and then the next one we're going to add a 1 minus 2r, 2r, and then multiply by t, and on this side we will multiply by r as well. Let me just go ahead and make sure this all looks a little bit easier, a little bit visually pleasing on the eyes. Okay, and next we'll need to go ahead and define those. So if we remember back to our matrix, we had the those last variables. So on the left-hand side of the equation, we had points where they would end up being at the very, very ends of our bar, where they're set values. And we had to add them to the other side. So for that very first value and that very last value of our vector, we had to add on an extra r times the temperature at position 0 and at the very last position. So what we need to do is say out of to our very first value in our b vector, we need to say that we're going to do b at that index point plus it will be r times t at 0. I need to make that a capital T. So it's going to take that temperature at that point 0 multiplied by r and then add it on. So it's going to be that additional data point that we talked about when we were at the whiteboard. And then we'll do the exact same thing except for the very last value in our b vector. So we'll index that by -1. And with that, we should be actually pretty good to go ahead and plot out our initial condition or our initial state of the bar. And I'm going to again just copy and paste this straight from up above, and we'll paste this down here. And we'll go ahead and just make this a figure 2, just to differentiate between the first two, or the first one. So we go ahead and run this. I need a multiplication here, multiplication sign. Let me just look over this real quick. Oh, that is wrong. That needs to be a plus. So in that array, we have 1 plus 2 times r. I think I might have said that wrong earlier. I apologize if I did. That's actually a 1 plus 2 times r, and then we have 1 minus 2 times r on the vector sides. So again, I apologize if I made that mistake earlier, or I misspoke earlier. We can go ahead and run this, and we see that we have the same initial state as before. That's exactly what we have up here, which is correct. That's not the issue that we had earlier. So it's good to see that this is working out and giving us the same results. So what we want to do next is very similar to what we did next up here. We need to iterate this over time. So I'm just going to go ahead and copy and paste all this again. And this will just give us a good foundation for what we need to do. So we can get rid of this. We don't need that anymore. That's the old method. That's what really messed us up. So we can delete that. But now we can use our solve banded. So we'll say solve banded, and we'll input our L. Our L value is 1, because we have 1 band below our main band, and we have 1 band above our main band. So U is 1 as well. And then next, we need to input our AB matrix, which in our case is given by the variable A. And then we need to input our B vector, which is given by the variable capital B. So there's our solve banded that we have. But you notice that we're going to be changing our temperatures. And while A here in Solve Banded is not dependent upon temperatures, it's not going to change as our temperature of our bar change, B will. B uses the temperatures within it. So we need to actually copy this over and put it in this loop. And that will allow us to, as we go through and reiterate and we get those new temperatures, we can go back through and resolve that vector so we have the right values. And in addition to that, I don't think there's too much more we have to do. We're going to leave the same modulus, so we're not plotting 2,000 lines. I will have to change this to figure 2. I'm going to leave all the names the same. There's no reason to change those. And we can go ahead and we'll display figure 2. So I'm going to go ahead and run this stuff from the top. And there we go. So that looks good. I believe this is the right graph. So let's go ahead and we can test it out by changing one of these values to make our R value greater than 1. So let's go ahead and change our delta T to, let's say, 5. And there we go. This does look very odd, and that's simply because we're taking so few time steps. As you see over here, we're going up to 10,000 seconds, so the time steps are very infrequent. The first time step is at 500 seconds, so we're not going to see as much. It's going to be a little bit more odd, but we're not getting that oscillation. So maybe if we knock down this this delta to, let's say, 1, that's a little bit more reasonable. There we go. So we see that we have a fairly normal looking graph of what we should be seeing. Again, it's similar to this, but now let's go up here and we can run this where delta T is now 1. And we see that we get these crazy oscillations. So, and then we come back down here, same variables, and we get this nice pretty graph. So that's the power of that Crank-Nicolson method that we did, and it shows you how we're now able to vary R so that we can vary R so that this is stable over all values of R, which is a fantastic and incredible feat. But that's actually going to wrap up this video and all the parts before it. So I want to say thank you for watching. I hope you learned something and have a great rest of your day.